Hey everybody, welcome to today's video about trends on the periodic table. Specifically, we're going to look at group trends and periodic trends for atomic size and for ionization energy. So hopefully you've had a chance to print off this template, and what I'd like you to do today is get two colored pencils, and with one of your colored pencils, I want you to fill in the electron shell diagram for each of these atoms, and in that same color, just kind of highlight these numbers right under the shell diagram, which is the atomic radius for each atom. And by the way, this periodic table looks a little different than most. It's not a full periodic table. In fact, the transition metals have been removed just for simplicity's sake. So what you can probably see as you're coloring is, first of all, within a group, a vertical column or a family, atomic size gets larger as you go down the periodic table. So that trend, size increasing as you go down the table, is really all about how many energy levels the atoms have. So in addition to coloring in the shell diagrams and the atomic radii, I want you to make, in that same color, an arrow over here, not just any arrow, but make it an arrow that's really fat down here at the bottom and skinny at the top. I think that'll help you remember the trend. So let's look specifically at three members of the alkali metal family. Let's look at lithium, that has 3 protons and 3 electrons, and then sodium, that has 11 protons and 11 electrons, and then potassium, 19 protons, 19 electrons. So when we look at the arrangement of the electrons this way, it's really easy to see that additional energy levels are physically farther from the nucleus. So, to describe this trend in size, these are the points that you would want to talk about, for instance, on a free response question. So as you go down a group, there are additional occupied energy levels, and each additional energy level is farther from the nucleus. And then furthermore, the inner energy levels shield the valence electrons from this Coulombic attraction of the nucleus. So let me just show you what I mean. In lithium, these 3 protons have a Coulombic attraction for all of the electrons, but it's their pull on the valence electrons that really determines the radius or the size of the atom. The electrons here in the core, in the inner energy levels, are doing a little bit of blocking or shielding. In sodium, the Coulombic attraction between the protons in the nucleus and the valence electrons is what determines the size, but now we have 2 inner energy levels that are shielding these valence electrons from feeling the full pull. And then in potassium, we have 1, 2, 3 inner energy levels doing even more shielding. That's called the shielding effect. And it is appropriate to mention when you're comparing within a group. All right, now I'd like you to take a look at the trend in size across a period. So if we look at this period 2 on the periodic table, notice that the size of the atom is getting very subtly smaller as we go to the right. That's the sort of surprising trend. So within a period, the larger atoms are over here on the left, and the smaller ones are over on the right. Let's look at 3 examples. Here's lithium. Here is carbon. And here is neon. So I've picked 3 examples from this period. Notice that in every example, that it's the second energy level that is being added to. And every one of these has one inner energy level. There's really no shielding effect here because the inner energy level for all of these members is exactly the same. But what is different is the charge. So lithium has a nuclear charge, that's charge of the nucleus, 3 protons. So a nuclear charge of 3, and by the way, we use the letter Z for nuclear charge. Carbon has a nuclear charge of 6, and neon has a nuclear charge of 10. And if you remember, Coulomb's law tells us that force of attraction between protons and electrons gets stronger when charge is larger. So, to explain this trend in size, we need to talk about what's going on with nuclear charge. As you move to the right within a period, nuclear charge increases. Coulomb's law says that force of attraction is stronger when charge is larger. So because of stronger force of attraction over here to the right, the electrons are pulled closer to the nucleus. All right. Now let's take a second colored pencil, and I want you in each of the boxes, I want you to color in the number right below the radius. I'm using green for this. These second numbers for each of the elements is the first ionization energy. Now remember that ionization energy is the energy needed to remove an electron from a gaseous atom. I put that in parentheses. Technically, the atom has to be, first of all, changed into its gas form, and then they measure the energy needed to remove. Now, notice that that is to remove an electron. And ionization energy is always talking about removing the easiest one. So whichever electron would be most easily removed, that energy is ionization energy. Okay, let's consider what we see going on within a group, vertical column. So we want to first of all make a note of how many energy levels. Do you see in this group that the ionization energies are actually getting smaller toward the bottom of the group? Or in other words, ionization energy is greater up at the top. Now this is going to be directly tied to how many energy levels are there. As we go toward the top of a group, there are fewer occupied energy levels. And the fewer energy levels would be closer to the nucleus. Let's look again at lithium, sodium, and potassium. So toward the top of a group, you have fewer energy levels, which are therefore closer to the nucleus. And Coulomb's law says that force of attraction is larger when distance is shorter. So in lithium, the force of attraction between these protons and the valence electrons is pretty strong because the distance is short. That's Coulomb's law. And the stronger the force of attraction, the more ionization energy would be needed to remove that outermost electron. In sodium, the force of attraction is kind of medium because the distance is medium. And in potassium, the force of attraction is weak because the distance is long. Okay, now let's look at our ionization energy trend going across a period. If you're reading these numbers that you highlighted, you're going to see there are some glitches. And we will talk about those anomalies at a later time. But for now, for the most part, we find that ionization energy increases as we go to the right. When we're comparing within a period, it's not enough to simply note the trend. If I said, who's got the stronger ionization energy, fluorine or oxygen? Okay, you wouldn't simply say, well, fluorine does because ionization energy increases to the right. That's simply restating the trend, but I want you to be able to explain it. So a comparison within a period is about nuclear charge. And again, as we go across a period, we see nuclear charge increases. And Coulomb's law tells us that force of attraction between the protons and those valence electrons gets stronger when charge is larger. So as the nuclear charge increases, the force of attraction increases, and therefore more ionization energy is needed to remove the electron. So take a minute to copy down those bullet points. And then let's just wrap up by remembering that if you are asked to make a comparison of atoms within a group, you need to consider what are the differences in the energy levels, and then use Coulomb's law. Force of attraction is weaker when distance is longer. Use that in your explanation. But if you're asked to make a comparison within a period, then you need to be looking at nuclear charge differences and use Coulomb's law, which says force of attraction gets stronger when charge is larger, in your explanation. Okay, guys, I hope that was helpful.